Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. Today we are going to talk about kinetics. In our last lecture we were talking about thermodynamics and we understood how to find out K value, the equilibrium constant value. We found out how to calculate the delta GF value, the free energy of formation. And then we found out how to calculate the standard free energy of a reaction and also the energy the free energy of a reaction at any other condition and the interrelations between activity, chemical potential, equilibrium constant and this Gibbs free energy value. Now, if you have any doubt related to those thermodynamic equations, if anything you do not understand, during the live course you can ask those questions and you will be receiving some assignments and you can practice during that time. Coming to kinetics, okay, so we understood that thermodynamics we are mostly trying to find out whether a reaction is going to happen or not. Okay, what is the energy conditions that will allow a particular reaction to happen in the forward direction, in the backward direction, and whether it is in a chemical equilibrium state or not. Okay. Now, as we have already discussed in one of the previous lectures, that equilibrium is dependent on the temperature, right. So, equilibrium conditions are very rarely found on the surface conditions of earth. It is more possible on the higher temperatures, that is inside the earth. Okay. So, if you are looking into the crustal reactions, reactions that are happening inside the earth's crust or those on the in the mantle, in the core, then you can say okay, so and so temperature, pressure conditions are met, equilibrium is reached faster and equilibrium exponentially increases with temperature. There is exponential function there. So, on the surface conditions, more than thermodynamics, it is the kinetics that controls the reactions. Okay. So, you not only need the thermodynamic, the energy aspect, you also need to understand the kinetics of the aspect, kinetics of the reactions. Okay. Kinetics by the term itself means that it will have a time related factor. It will have a time related factor. We are going to check the rate now, how fast a reaction is happening, how slow a reaction is happening. In fact, more than the fast reactions, the slow reactions are important because the slow reactions are our controlling reactions. Right. It is the controlling reaction which is our rate determining reaction. The slowest reaction is our rate determining reaction. So, with this small introduction I will begin this lecture today. So, kinetics concerns itself with the path the system takes in achieving equilibrium. Thermodynamics allows us to predict the equilibrium state of a system. Okay. It will just tell us okay, reaction will happen, forward direction it should go, okay, no, right now the equilibrium has been reached, forward and backward reaction rates are equal. Okay. So, these kind of information thermodynamics will give us. Okay. Kinetics will tell us how fast equilibrium will reach, how fast the reaction will move in the forward direction, in the backward direction. Okay. So, since kinetic concerns itself with the path, therefore, we will use this particular term called a reaction mechanism. It is not only one reaction, but the entire mechanism of the reaction we need to now evaluate. Okay. Because now this microscopic perspective becomes essential in understanding how the reaction mechanism is working. What all are changing during the reaction? These microscopic perspective will give us an understanding why is it moving fast, why is it moving slow. If it is moving slow, then is this the rate determining step? Okay. Chemical systems, the aquatics, okay, the chemical aquatic system always is governed by both thermodynamics and kinetics. Okay. So, you not only need to know what is the reaction, whether it is a equilibrium condition, not equilibrium situation, you also need to understand the reaction mechanism. So, this understanding of reaction mechanism is of paramount importance here, and for that you need to very carefully we need to follow how the reaction is happening, what structural changes are going on, what things are happening during every reaction step. We have to find out that, because if we are missing on anything in this step, we are going to finding out what is the kinetics. We are going to not be able to correctly determine that. Now, since we are talking about time scale, right, we are going to this is just a glimpse of the time scale, how it is moving. So, here you can see there are two divisions, one is the residence time, one is the T half, that is a half life, T half time. Okay. So, precipitation reactions, okay, they can happen very quickly, it can be from within seconds to few minutes, okay, maximum it can reach to some hours. Okay. That is a residence time of precipitation, that is precipitation reactions that is happening, right. Soil moisture reactions that is happening, that can be variable, highly variable. So, it can vary from some minutes or to years. If it is continuously raining, there is a lot of soil moisture always available, the reactions go on forever. Reactions happening in lakes, streams, groundwater, you can see the differences. Stream, it is a fast moving system, right. Therefore, the residence time in that system is low. The reactions that is happening there, that compounds are getting exchanged faster, the residence time is less there, maximum 5 to 15 days, okay, depending of course on the catchment area. If it is a small catchment, very fast turnover. If it is a very huge river, it can take several days from the starting point to meeting the ocean. Okay. Lakes, again it is an enclosed system, it depends on whatever is slowly where the lake is, what is the end point of that lake. It is definitely if from there, if there is an inlet that is going out joining some river or not. Okay. So, that determines again the residence time of that lake. Groundwater, shallow, deep, all that, if it is a deeper groundwater, the residence time can be in several thousands of years and even millions of years. Shallow groundwater, it can be very fluctuating, within seasons it can vary, shallow groundwater. In terms of reaction rates, okay, T and half, okay, the reaction rate is T half. Okay. Now, that reactions are happening. So, the solute water, whatever interaction is happening, that is happening in few minutes, seconds to minutes, that is happening. Gas water exchange, within few hours it will reach the equilibrium. Okay. Hydrolysis reactions can take a long time. Okay. It depends on what is interacting, what is continuously exchanging. So, it can start from minutes and can go on forever. Adsorption, desorption can happen very fast and can go on, this is highly variable. So, they are given dotted, it can go on, depends. Mineral water equilibria, mineral recrystallization takes a longer time. For minerals to recrystallize, it can take from few days to few years or maybe millions of years. Okay. So, there is a wide time scale that you can see the different processes are acting, right. Let us move into understanding the reaction kinetics, a reaction mechanism. Okay. First thing that we are going to try to understand is the difference between elementary and an overall reaction. Okay. Say there is a example we have taken. Okay. Consider this is the weathering of anorthite. Let us consider this example, that of weathering of anorthite. We are going to write this overall reaction. So, the overall reaction we can write as calcium. So, this is a calcium aluminum silica mineral. Okay. So, this is my anorthite, okay, it is a mineral. It is going to react with water and carbon dioxide, it is weathering, right. So, its anorthite is naturally found in any of the feldspar rich rock. Okay. Anorthite is a type of feldspar. Okay. So, anorthite being a feldspar, you can find it in any type of silicate rock and mostly granite and all that, very common mineral, and that is getting weathered. Weathering agents are my water, my carbon dioxide that is dissolved in water will form carbonic acid, slightly acidic, it will react with the mineral. Okay. This reaction will produce two products. Okay. One is my calcium carbonate, another is aluminum hydroxide, and another is silica quartz. Those are my final products, that is calcium carbonate, aluminum hydroxide and silica, that is in the form of quartz. So, silica can exist in different forms, opal, quartz. Okay. Quartz is the most stable form on earth's surface conditions. So, quartz, it is very difficult further to weather quartz, very hard and stable mineral on earth's surface. So, these are very stable now on earth's surface, it is very difficult now to weather them like quartz and all. Now, this is my overall reaction, anorthite weathering to calcium carbonate, aluminum hydroxide and quartz. This is the overall reaction. But if we are going to consider the kinetics, we are going to consider all the steps that anorthite has taken, that carbonic acid starting from formation from carbon dioxide dissolution into water has taken to form all these products. Now, let us break down this reaction. Okay. So, the first thing that we are going to write is H2O plus CO2 gas will, so the CO2 gas will dissolve in water to form carbonic acid H2CO3. Okay. Now, this H2CO3 again is not stable, it will break down into bicarbonate and H plus ions. Okay. Now, this anorthite will react with water and in presence of hydrogen ions, it will form Si2Al2O5OH4, which is actually called another mineral called kaolinite. This is another clay mineral. Okay. This is another clay mineral, kaolinite, and it will release calcium during this process. Now, again H2O will react with kaolinite to form quartz and aluminum hydroxide. Bicarbonate again will dissociate and it will form carbonate ion and H plus ion. Now, this carbonate will react with calcium and it will form calcium carbonate. Okay. So, this is the breakdown of that only one reaction. So, this is the breakdown of that one reaction. Now, again note this one, step 1, step 2, step 5 and step 6. These are elementary reactions, that means two simple things is forming one item, right. This two reactants is forming one product. Again one product or one reactant is forming two products, or these two reactants is forming one product. So, this is called elementary reactions, that means there is no further breakdown of this step. But step 3 and step 4, this has more than one reactions. Okay. So, these products we can see how these can again be broken down into subsequent elementary reactions. Okay. So, these are the non-elementary steps and these can be further broken down into elementary steps. So, from step 3, okay, we are going to break down the step 3. Okay. So, from here anorthite we are going to move. So, anorthite plus 6H2O plus 2H plus will give us silica dissolved aqueous plus aluminum hydroxide aqueous, calcium 2 plus and hydroxide ions. Now, this silica which is dissolved and again there will be a reaction with AlOH and that will now form my kaolinite. So, that step 3 can again be divided into two reactions and again this two reactions, the second reaction can again be broken down. So, SiL2O5 plus 5H2O. So, this particular reaction, the step 4, okay, this step 4 okay, is forming quartz and gibbsite. Okay. So, this one again we are going to break down and here we are trying to understand okay, how Si2 is changing. Okay. First Si2 when it is forming as opal, okay, but opal which is not stable at the earth's surface conditions will change to SiO2 quartz. Okay. This will change to SiO2 quartz. Okay. So, from that simple one reaction you see we could derive another 10 reactions, right, and kinetics is to understand all these reactions even more in detail. So, we are going to see structural changes. Okay. So, for example, in the step 3 the breakdown of anorthite to form kaolinite plus a free calcium ion, a lot of structural changes is happening, right, structural changes are happening during this breakdown. Similarly, the breakdown of kaolinite to form quartz and gibbsite, that is also having a lot of structural changes. Okay. And precipitation, phase transformation, this one, this is phase transformation SiO2 from opal to quartz. This is a phase transformation, that means there is a lot of structural changes going on. Okay. So, all these structural changes, any particular step can be slow, that will be my rate determining step. The slowest step will be my rate determining step. Okay. Now, such description of the overall reaction in terms of elementary reactions is called the reaction mechanism. So, we will give you a big reaction, but you have to break it down and write it in terms of elementary reactions, okay, to understand the reaction mechanism. If the reaction mechanism is not clear, if it is not correct, our kinetics, understanding kinetics can get complicated. Okay. An important step therefore, is to determine the reaction mechanism. Okay. And many times there can be different paths for an overall reaction, and several paths may be simultaneously involved. Therefore, it can become quite complicated. So, we always have to experimentally determine which is the most favorable path, right, which is the most favorable path, and in aquatic systems it becomes very complicated because you are not in any controlled situation. There is n number of factors that is mixing happening, okay, biotic interaction, organic interactions, okay, all the elements that is there together. So, experimentally we can do in the lab, we can separate out, we can see, okay, this is the best possible path that is there. And kinetics can only provide an accurate description of a process if all the paths are known, and you determine, okay, these are the paths and this is the best path that will happen in this condition. Now, how do we write? As I said, in terms of kinetics, we are going to talk in terms of rate of the reaction. Okay. So, we are going to determine this term called rate of reaction. Okay. So, for example, there is precipitation of dolomite from a solution. Okay. So, the reaction is written as calcium plus magnesium plus carbonate is forming calcium magnesium carbonate. Okay. And how is this rate written? The rate of the reaction, which is denoted by this R, is written as R is equal to delta, that is dCaMgCO2, that is the dolomite, divided by dt. So, how much dolomite is being produced in this dt time, okay, that is the rate. Now, for every mole of dolomite being produced, 1 mole of calcium and 1 mole of magnesium is getting consumed, and also 2 moles of carbon dioxide, sorry, not carbon dioxide, bicarbonate, 2 moles of bicarbonate will also be consumed to produce 1 mole of dolomite. Therefore, R could be expressed in other terms also. Okay. So, rate R can also be written in terms of dCO3 2 divided by dt, and this is having a minus sign because it is a reactant, it is decreasing over time, and whatever is the stoichiometric coefficient here, that will come as the denominator. Okay. That will come as the denominator here. Here also same. So, R can also be written in terms of calcium. So, R is equal to minus d calcium concentration divided by dt. Again it can be written in terms of d in brackets magnesium concentration by dt, and these all are equal, the rate is same. Okay. All these are equal sign. Okay. These are equal. Okay. These are equal signs. Okay. So, it can be written in terms of any component, okay, either product term or the reactant terms. So, how do we have the general equation? Let us look into the general equation now. So, the general rule is, if you have this reaction, say A plus B, which is forming C plus D, and these are the stoichiometric coefficients, then the reaction rate R is defined as in these terms. So, is equal to minus 1 by A of dA by dt, again equal to minus 1 by B of dB dt, minus 1 not minus, this is the product So, these are in positive terms. So, 1 by C by dC by dt, which is equal to 1 by d dd by dt, and these are the concentration of the species. Okay. These are the concentration of the species, and again positive and negative depends on whether it is the reactant or the product. Thus, the rate of a reaction is simply the rate at which a reactant is consumed or the product is being produced divided by its stoichiometric coefficient. This is very important, okay, that there has to be balanced stoichiometric coefficients. Okay. Now, another term we are going to introduce, which is called the rate constant. Okay. K is the rate constant, R is reaction rate, K is the rate constant. R is equal to K, and if you are writing in terms of activity, okay, then activity of A into activity of B into activity of C into activity of D, and all of them are raised to the power of n. What is n? N is the order of the reaction. Okay. N is a very, very important term called the order of the reaction. Okay. And it can be any value from 0 to any bigger number. Okay. And we are going to determine this n value, that is the order of the reaction. Okay. So, again this is the reaction rate, small k is the reaction constant, and these are the activities multiplied for all the products and the reactants and raised to the power of the order of the reaction. The order of the reaction we are going to determine. Okay. Now, reaction order is an expression of the dependence of the elementary reaction rate on the concentration of the species involved. What does it mean? Like whether a particular reaction is dependent on the concentration of a particular product or a reactant, that is what we are trying to search. Okay. That is called the reaction order. Okay. Say for instance, you have this equation A plus 2B is producing C. If the reaction is independent of A, it is called 0 order with respect to A. What does that mean? What does that mean physically? What does it mean that a reaction is independent in terms of A? It means that if I change the concentration of A, the reaction is not going to increase or is going to decrease. The addition of more A, by adding more A, I am not going to make the reaction any faster. Then that is called that the reaction is independent of A and its order is 0. Again, for example, if by increasing the concentration of A, I see that the reaction is directly increasing and is proportional to the concentration of A, then I will say that the reaction is first order to A. Okay. It will say, if I again physically think that if by increasing a particular component, say A, if by increasing that reactant, my reaction rate increases, then I am going to say that the reaction is first order to A. If my reaction is dependent on both equally, okay, both A and B equally, that means if I increase A also, it is increasing proportionally the reaction rate, and if I increase B, then that also is increasing the reaction rate proportionally. Then it will be a second order reaction. We are just going to add the reaction orders of individual reactants. Okay. If my reaction rate for A increases exponentially rather than proportionally, again think about the difference. One is increasing proportionally, then it is first order. If it is increasing proportionally, then it is first order. If it is increasing exponentially, then it is called a second order reaction. Okay. Then then the reaction order changes from 2 plus 1 is equal to third order. So, the reaction overall order of the reaction becomes 3. Okay. So, how do we know what is the reaction order? For that, understanding the reaction mechanism is very important. Okay. Understanding the reaction order is very important. Okay. So, this is again given in different terms. So, if there is another equation, that is A plus 2B plus something something some other reactants is producing some other products, that is P plus 2Q plus again some more products, then what is the reaction rate, the R term? R is equal to dA by dt, okay, dA by dt, okay, minus dA by dt, it is actually equal to R is equal to minus dA by dt. Now, if I multiply minus on both sides, so minus dA by dt gets positive, and that R is also equal to K into all A, B, P, Q, all the terms raised to the power of the stoichiometric coefficients, right. Now, dA by dt, since now this is the disappearance rate of A, it is a reactant, okay, and K is the rate constant, A, B, P, Q, these are all again individual reaction order constants. Now, today I will stop here, and in our next lecture we are going to discuss how to determine what is the order, what is these values, how to determine the order values, okay, because that will give us the reaction order of the entire reaction. Okay. See you in next lecture. Thank you.